Hello everybody, this is Stefano Barrios Pompey, and I'm here to talk to you about my final project for non-interactive computer graphics at Northeastern University with Professor Mike Shaw. What is ray tracing? Ray tracing is a computer graphics rendering technique that's used to simulate the way light interacts with objects, and it's used to generate very realistic images. What is a bounding volume hierarchy? At a high level, this is a data structure that's used in graphics and computational geometry to help optimize collision detection and, specifically, ray tracing. You can think of it as an algorithm that basically takes all the objects in a scene and puts a box that encompasses all the objects. And it is minimally big to cover all of the objects within the box, but it doesn't have anything else outside of it. The idea is that this will help increase the speed of our intersection tests because if a ray is shot and it doesn't intersect with this bounding volume, then there's no need to do any more analysis and we can move on to the next pixel. To put these final optimizations to the test, I decided to put them side by side and render some scenes, one with a BVH and one without. And as we can see for this Cornell box, it's pretty low resolution, it's pretty noisy at 400 by 400. But I thought this was more than appropriate just to test how long it would take. Both came in at about 2 minutes. You can see that they have the same raised cast, the same bounding volumes, intersections. And so the idea is this is not a very complex scene. Really, it's two boxes, a light source, and a couple of flat planes set up to make it look like a room. We'll get to learn this with BVHs, but the more complex the scene is, the more helpful it will be. There is quite a lot of overhead involved with creating the whole tree hierarchy, and so sometimes if a scene isn't complex enough, it may be even worse off to implement a BVH. In this much more interesting and fun scene, this is where we really see the benefits of the BVH. We can really see the magic of the tree structure come into play here, where the ray test is going to discount a lot of empty space simply because it knows where all the objects are. It's able to cut down all of the checks it's doing by half each single time because it's going through a tree, and so that's going to highly optimize the way the ray intersection tests are conducted, irrespective of the material or the type of geometry it is, whether a sphere or a triangle. And again here in this more simple scene, we can see that with a BVH, it's about 20 seconds to render this, and without, about 14. As I said previously, because we are constructing a huge data structure, that is going to take some time and some overhead. In this particular case, it may seem a little bit trivial, but if you're looking for a very simple ray tracer, you can save a lot of time and headache not implementing a BVH, and you'd likely get faster results. But if this is something you want to build on top of and you want to scale it, a BVH is definitely a worthwhile investment. So now I will take you through a live demo of my code. So this class represents the BVH, and it includes some headers, some includes. We define the class, which is a subclass of the hittable, meaning that it can be treated like any other object that can be hit in our scenes. Each node has two left and right children and an axis-aligned bounding box, which is how we're going to keep track of where we are in the tree and the box containing the objects themselves. We have a couple different constructors, a couple different methods. Notably, we want to look here at snippet of code, which is responsible for constructing our BVH recursively. And so it can check for one object, two objects, but it soon enough becomes a little more complex when there's multiple objects. That was a quick overview of our BVH class. And so what I'll do now is I'll go ahead and render the random scene, which is the same scene that we've seen at the end of book 1. I'm just going to make sure that we are getting a fresh copy of that render. And so I will let that run and come back when it is finished. Okay, so now we have finished rendering. So I'm going to go ahead and open up our fresh ppm file, which is going to contain our rendered scene. And one thing I did want to note, you'll have to trust me on this, but in the slides there are two different pictures, one for with the BVH and one without. And I can promise you they are almost virtually identical. This optimization algorithm really reduces how long it takes to render, but doesn't provide any visual issues as far as I'm concerned, which is very useful. The nice thing is that these functions return worlds that we're going to use as our scenes to be rendered. And if we want to use a BVH, all we really need to do is put that world into a BVH node. And the rest will be taken care of, which is very nice. Otherwise, for anything that's smaller, just a couple of objects, you can just return the world itself. So as a brief recap, we have built upon Peter Shirley's weekend ray tracer. We have included an optimization in the form of a bounding volume hierarchy, and that allowed us to speed up the ray tracer. The nice thing is this is completely written in C++ using our own libraries, so all you need is the standard library. And you should be good to go. If you'd like to take a look at this and play around, please feel free to check out my GitHub repository for the code. One difficulty that I did want to talk about is Crash Bandicoot. I found an OBJ file of his model, and I would have loved to import him and have him join us along in our ray tracing adventure, but unfortunately I was not able to get that implementation in for the final project. So sorry, Professor. I believe the biggest struggle I had was honestly just parsing the file. And up until this point, I have a working parser. It actually goes into a class, a 3D mesh object class, and it works just fine. For some reason, it just does not want to render. Perhaps it's a problem with how I'm mapping the material to it, but that is something that will be dealt with over the next couple weeks. Again, thank you guys very much for your time. It's been a pleasure taking this class with you all, and I hope you all learned, and looking forward to continuing our ray tracing adventures in the future. Thank you.